Hello and welcome. In this video I'm going to be doing a deep dive, a code overview of my system as I have it so far. I'm not very good at doing brief descriptions, so what I'm going to do is sort of spiral. I'm going to have a very brief top level description and then I'll gradually go into the weeds. To start with, just a little word about my project. So I've been working on a platformer, 2D platformer, as if there aren't enough of those around already, but I am trying to give it a unique look and a unique story. Now, as far as the story goes, still in the draft stages, but I've shopped it around and people are happy with it, I think. So once I'm really happy with that, I will be putting up some sort of Steam page or something. Also, I've got this camera here because my Asus Craptop is not really capable of recording video OpenGL stuff. It sort of stutters. The reason I chose this laptop for this development is in order to really optimize my system. If I get this working on a clunker like this, it should pretty much work on anything. Also, every day I've got this little scratch pad where I write little to-do items. I don't get them all done every day, but planning things out on paper is really useful. But I have delayed enough, so into the actual system. So this game system is data oriented and it's based around the entity component system architecture. The way that works is, just imagine a database and a whole bunch of tables. Your entity is an unsigned integer. It's basically your primary key in your database. A component is a little tiny chunk of data. So if we go down here, these are some classic examples. If I want something to have a position, I will give it a transform component. This tracks the object's position, whether it's facing left or right, its scale, because I may need to scale things on the fly. If I want things to collide, then I'll give them an AABB component, an axis aligned bounding box that has a minimum corner and an extent. If I want things to move around, I give them a physics component that has a velocity, it has a collision layer. When things move around, I only want them to interact with certain layers. So when the monster moves around, for instance, it doesn't care about running into items, that's perfectly fine. Just imagine a component as a little tiny chunk of data, and then I have these component sets. Say, for instance, I have a component set of all of the transform components. That's a table which says, hey, for this primary key, for this ID, this is the corresponding transform component. What that table does is it maintains its list of transform components in sorted order. Now, using binary search algorithm to look up entries in the table, and I figured that I would be looking things up a lot more frequently than I would be inserting and removing. So there we have it. That was the decision made there. Wrapping everything up, the game is like a really big state machine. So I have this convenience structure called a component registry, which holds all of the tables in the database. Jeez, why am I coughing? Anyway, so for instance, we have a component set of transform components, a component set of static render components, a component set of skeletons, animation components, and all of these things. And these tables are not passive things. The presence of an entry in a table is a direct request that something must be done with it. So if I have a set of animation components, every single one of the entries in that table is requesting to be drawn on the screen. It's requesting to be animated every frame. It's super important. So again, We have our components, which are little chunks of data. We have component sets, which are like database tables, and then we wrap all of this together in a component registry that holds all the tables in the database. Controlling all of this, we have an app. So here's my app. It holds a component registry. It also holds a bunch of systems: animation, skeletal, render, input, all of that. So when the app starts, what do we have here? Factory. I'll get to factory in a second. But the app starts up and it has its component registry, so it has its state of the game, and it goes ahead and makes the systems. And when it makes each system, it throws in all the information that that system will need to know about. In most cases, it'll just need to know about the component registry. When a system is made, when the system is made, it immediately captures that reference to that component registry so that it can later query any information about the state of the game as needed. So for instance, let's say we want the world to update. By the way, the world is sort of a combination of a physics system and a collision system. That's just how it is. When the system needs to update, it immediately has access to the relevant tables. It can look through them, so it does a direct look through every single one of the physics components, grabs the information it needs. Now this is what I would call the primary table. Okay, the primary table is the entries which we know are contiguous in memory. Like we know that every single physics component, we're going to need to do something with it. We're going to step through that linearly, one by one. But then we might need additional information like, the transform, the collision AABB. These are indirect lookups. Provided that we have the ID of the object which is moving, that primary key will match with entries in other tables. So I know I'm really butchering this explanation, but it's a bit freeform. So we say, hey, this ID might be the number 3 or something, corresponds to an object which is moving. So let's grab the corresponding transform and hitbox for ID 3 from other tables. That's fine, it's composition. And then we do what we need to do, various calculations and things, and then we update that corresponding component in those other tables. So I think that's the broad overview of the stuff. Oh, also there's a factory. I'll talk about that because I'm really happy with the implementation of the factory. So the job of a factory is to make or destroy things. And what that comes down to really is inserting the right data into the right table. Let's take a look at, make Alice, make the player. Because originally I was just playing around and doing a sort of an Alice Madness Returns clone, from which I have deviated. Different story now, different thing. But anyway, when we go to make an object, that object will need to go into a number of different tables, depending on what we're making. For the main player, it's quite involved. For simple objects, it's much simpler than that. But anyway, the next stage is we go ahead and initialize an entry, initialize a component based on data from the file that we just read with some little tweaks and things. And then we go ahead, we fetch an ID to represent the object, and then we insert into each table the component. So one of the big things that I did recently is I unified the animation system so that animation objects themselves are like game objects. It's just, does that make sense? They get inserted into tables is what I'm saying. So let's have a look, for instance, at the main player animations. I'm going to have what's called an animation description, and an animation description holds information like, hey, for this given sort of animation, what object are we animating? What animation, like what action are we doing? How long is the animation? How many frames? After this animation plays, which animation should play next? It's a top-level description of an animation. So what we can do is we can go ahead and build these various animations, and each of these constructors returns the entity corresponding to that animation, the ID of that animation. And then knowing all that info, yeah, of course, we can then, I have this reverse lookup table so that for a given object type and animation type, I can quickly retrieve the ID of that animation. That's useful in that's useful in logic. When I press a button to move a character, I want to quickly know, hey, which animation ID should this character now have? But knowing all of that, we can then build descriptions. So for instance, when we walk, we want to keep walking after that animation plays. We want that animation to loop. Whereas when we shoot, the next animation after that needs to be the idle animation. Well, in order to do that, we need to have all of those animations already inserted into the database, and we need to have references to those insertions. Let me talk a little bit about the skeletal and animation systems. Now, as I was talking about before, this is a top-level description of an animation, but we also have an instance of an animation, so like an animation component. So a game object will have a given animation component that will have a global frame number, so to speak, as well as an ID of the animation object which is being referred to, and that animation ID refers to these animation descriptions, and so on. The object will also have, or the animation will also have a bunch of keyframe spans. Now, a keyframe span is pretty much what it sounds like. It's a point between two keyframes. So keyframe span will have a number of frames for its duration. It'll have an ID, which refers to the next keyframe span after this span is expended, and it will have a target, that's a bone. Yeah, every span just affects one bone, basically, and the bones just rotate, that's it. So we just have, angle A, angle B, and this span sort of, its job is to interpolate between those angles. So really, a skeleton is something which can be animated. It has a set of bones as well as a set of playheads. A playhead has a current time and a current span that it's working on. So when we see a skeleton and we know exactly which bones and playheads are active, we get the current position of each playhead. We use that to interpolate the rotation on each bone. We use that to set the angle, the rotation of the current bone. That's this theta. And then that's the job of the animation system. All that does is just sets the rotation of the bone. And then later on, in the skeletal system, what happens is, given this information about the bone's position, angle, and all that, as well as its children and stuff, I'll need to update that. Get rid of some redundant data. Anyway, apart from that, the job is basically to build the transform matrix. The transform matrices are then uploaded to the shader, and then for each vertex which is being drawn, it knows which bone it belongs to. Every vertex just belongs to one bone, and it uses that bone's local transform. Another feature which I'm particularly happy with is I'll bring this up, the world's collision system. There are a bunch of different objects which we can possibly collide with, but the biggest one is just static blocks. Static blocks block motion for everything, and in my game, at least currently, they're never going to move. And so what I'm doing is, instead of having static blocks as AABB components in a general database, what I'm doing is I'm baking them directly into the world, because that's the only place they're being used. The world can do queries like, hey, can this thing move? And so it has its own inbuilt data representation. One thing we can do is we can send a message to the world and say, hey, add this box. No problem. The world has a set of blocks. What it's going to do is it's going to look through those blocks, and for each block, it's going to say, hey, this box that I'm adding, could that possibly merge onto that block? And if that's true, then what it will do is remove the block that exists in its data that it's going to be merged with, make a box which is the merge of the existing data structure and the incoming box, and then retry. Because possibly after merging with one of the existing blocks, this merged block will then merge with one of the other existing blocks. I know this sounds like ramblings, but the thing that I really like about this is this bit here just speeds it up a little bit. If I remove this line, remove these lines, it'll just naively add everything, it'll still work. But if I include these lines, it'll do the same thing, but we'll have a fewer number of blocks and collisions will be sped up. Okay, so here we are in our system. We've got a few controls. Currently we're in what I call dev mode, so we can just use arrows to move around, although that is being thwarted by the camera panning system. That's okay. Just hit Y to get out of dev mode. We can go ahead and move around, space to jump. And yeah, but the thing I want to get into is if we go into dev mode and zoom in, we can see that these blocks have been merged where possible. Particularly visible here. So these blocks down here have merged horizontally. These blocks here have merged vertically. I'll just get rid of that. And if we like, the thing that I'm getting at in a very roundabout way is I'm trying to design the systems of the game so that they are modular, so that I can swap something out for a more fine-tuned system and it will still work. This makes it much easier for me to revisit things later on and tweak them. Yeah, so now if we zoom in here, we can see that these blocks have not been merged, but the frame rate is down. And by the way, just so you can see, like, what would a code review be without a little flex? But if I switch this into release mode, it will take a while to compile. But one of the things is I'm using a lot of standard containers, like standard vector and stuff, which have a bunch of performance checks in debug mode. So if I switch this into release mode, we can really see the power of the system. Ooh, not that good. Okay, well, take my word for it. When I was running this without OBS, it was reaching close to 700 frames per second. This is pretty good. We're walking around 400 frames per second on the Asus crap top. I'm pretty happy with that. Yeah. Okay. I guess the only other thing I was going to talk about was textures. So I'm using texture arrays for all of this. What that means is that all of these different sprite sheets and things are loaded in as one texture, as one virtual texture. We actually have sort of, if you're not familiar with it, texture arrays is an OpenGL object which has layers of textures. So let's say we have the player sheet gets loaded in as one layer, and then the monsters get loaded in as another layer, and then the items get loaded in as another layer. But that all counts as one quote-unquote texture in OpenGL. And the benefit of that, firstly, is that for each of these individual items, be it a coin, a flower pot, a jumping pad or something, we only load that image once. So here my memory usage is about 98 megabytes. Before it was like 300 megabytes. So that's good. And then secondly, when we go to draw things, we only need to bind a texture once. We don't need all of these individual, GL bind texture calls, because it's just the same quote-unquote texture for all of these objects. The fewer OpenGL calls we can make, the better. And yeah, I mean, this has just been sort of an off-the-cuff dive into the systems. I hope that you enjoyed it. I hope that you got something from it, because sitting here explaining it, I sound like I'm losing it. I guess I need more coffee or something. But yeah, I mean, ask me if you have any questions. That's how it works at the moment. And that is it for me. So have a good one. Happy New Year, as I said in the last video, and I'll see you again soon. Bye.